module 5 we have discussed many of the materials which show interesting properties both from electrical resistivity point of view, and also how some of these materials hold the key to electronic properties based on the magnetic response. So, in the first few lectures we have discussed about colossal magnetoresistance. It is mainly to do with oxides where the resistivity is basically fine tuned by the magnetic transition, and we have also looked at two other applications, namely GMR and TMR. Those are actually not the material's intrinsic property, but those are extrinsic property dependent on the interface of the multilayered structure and how this magnetic alignment of these layers across the interface can define the electrical property, and those are specially rich features because they affect the applications to a larger extent. And we have also seen another extremely illustrious candidate, that is a high temperature superconductor in the form of oxides, how they have shown unusual properties mainly coming from defect chemistry. And the class of superconductors that we have seen are mainly highlighting the importance of what can happen within one unit cell which can affect bulk phenomena such as metallicity in metal oxides. Today I am going to attempt on a larger issue of carbon family, because in the last 15 years the number of publications that has been generated because of the new adventures that have gone through in this carbon family has almost overtaken any other field, and this carbon family has also is another very important interface which has brought biologists, physicists, chemists and engineers together. This is one of the another important milestone other than the high temperature superconductivity and colossal magnetoresistance, which has brought interdisciplinary approach into our modern research. So, I would like to place all these issues on record, because if we really look at some distinctive innovations or discoveries which has come, which has almost shaken our research activities across the world, I would say that this is the most important and third most important milestone in the last 25 years. The first slide also sums up the complexity, because it is not possible to just represent one structure to define what this carbon family, new carbon family is. As you would see here, it is all about a black stuff that is coming, and that black stuff can be anything. It could be in the form of a ball, which we call it as fullerene, or it could be in terms of a wire, which we call it as carbon nanotube, or it could be as a sheet, which we call this as graphene. Now, to just bring to your focus what is hidden here, it is not just the shape, but it is the dimension that has progressively changed. And to understand all these three new allotropes of carbon is absolutely impossible to cover in just one lecture. So, in this lecture I will try my best to bring essential features of each class and try to see whether we can get some comprehensive picture of all the three discoveries that has come through in the last 10 years. And this is just a few milligrams of carbon, which is actually carbon nanotube which a person is holding, and this little amount of carbon can actually cost you several hundred thousands of rupees or dollars. So, it is so expensive, so important, and we will see in the next few slides what are the rich chemistry that is hidden in this compounds. Just to highlight how much we have transcended in this research in terms of dimensionality, all we know is the most familiar 3-dimensional carbon, that is graphite and diamond. Both the chemistry of it and the practical applications of it we know. So, I do not want to dwell more into it, but after 3D we have immediately come across the 0-dimension carbon, that is nothing but fullerenes or buckyballs. They are actually in the form of a football, and if you look at the symmetry, if you take a icosahedron and then try to chop off the apical carbons, then you would be able to get this buckyball or the fullerene. And therefore, if you look at this is of a higher symmetry, icosahedron has the highest symmetry, and in this symmetry you call this as a 0-dimension, and also the confinement of this size is very few nanometer. Okay, so from 3D actually we have transcended to 0-dimension, and in terms of the history of the invention, from 0-dimension we have transcended to 1-dimension, that is single wall carbon nanotube or multi wall carbon nanotube, and from 1-dimensional carbon recent discovery holds lot of promise on the 2-dimensional carbon, that is graphene. This is realized in 2004, and now you would see on a comparative scale graphene is actually going to take over the whole industrial applications because of its rich physical properties. Now, what we need to understand as we go from a 0-dimension to 2-dimension, these are the new manifestation of carbon. Until recently, even in the school textbooks, it was written as the 3rd allotrope of carbon, which is graphene. But now if somebody has to write, or history makers have to recorrect, that we now have at least 5 manifestation of carbon, including the 2-dimensional graphene and 1-dimensional carbon nanotube. But basically I want to bring another essential feature. If you really look at the structure of how this fullerene or this 1-dimensional carbon nanotube evolves, you would understand that it is basically made of the 2-dimensional graphene sheet. So, you can build up on a single wall carbon nanotube or a 1-dimensional carbon nanotube, basically understanding how to roll this carbon graphene sheet, or if by some means you can scroll it up into a buckyball, the basic unit then happens to be that of a 2-dimensional graphene or graphite sheet. And as you know, graphene is nothing but graphite, only thing it is actually sliced. So, when you slice these layers, then you result in a graphene sheet. So, it is as simple as that, but then the technology was not to its maturity that such 2-dimensional layers could not be achieved. But now we have a way to do that, and we will also look at the chemistry behind how to make this graphene sheet. So, this is the paradigm shift that we see in this carbon research, and therefore, we can very confidently call this as a new family of carbon. So, in this lecture I will highlight to you starting from a 0-dimension fullerene, and I will dwell little bit more on 1-dimensional carbon nanotube, and then I will look at some of the details of 2-dimensional graphenes. Just to highlight one more point, this curve which is shooting up is actually the amount of publication that has gone through in the recent past on carbon nanotubes compared to the fullerenes. The fullerenes is here, and then you can see a sudden upsurge here for the graphene. Graphene has just hit the news, and therefore, graphene is going to really transcend, but overall the major focus among all these three has been carbon nanotubes, because it has been well established now even in terms of applications. So, just to give you idea about how the global research is positioned now, you have lot of activities mostly on carbon nanotubes compared to fullerenes. I cannot resist by introduce these two people who actually have been involved. Along with them, Professor Kroto also is given the distinction of being one of the Nobel laureate, but first person who really hit the news is Dr. Richard Smalley from the Rice University, but with profound sadness I should also say that he succumbed to cancer few years back. So, he is no more, but he was the person who really found this Buckminster Fullerene. He isolated it along with Professor Kroto, and this is the picture of the buckyball that they isolated from Rice University at Houston in Texas. And here is another person, he is actually electron microscopist, and he was not a synthetic person, though he is basically electron microscopist. All he did was a very careful investigation of the fullerene which was made, and during his electron microscopy studies he found some images which became very prominent, and that was the cause for the discovery. But what really brought the fullerene to focus is this simple cartoon, which otherwise would have missed the whole lot of discovery. I want to just emphasize the curiosity that we need to have in doing research, and in this case what is what you see here is the mass spectra which gives just one single M/E peak ratio for this fullerene, which does not come in 0 to 100 ME, it is beyond 500 ME, which usually we might be tempted to ignore, especially when you talk about carbon clusters. You would not like to look at a higher M/E ratio, and this is a M/E ratio comes beyond 500 mass, and this single peak actually brought the discovery of fullerene into focus. Otherwise there was no way they could map it. So, every characterization tool in material synthesis is of great importance, and therefore I would like to stress how this discovery in the first place was made. And then because of the curiosity that was generated in fullerene chemistry, the single walled carbon nanotube was found, and as you see from this cartoon below, that there are different layers that or different layers with different color purity you can see, but each of this layer actually is a composition of carbon nanotube, but with different wall diameter. So, this wall diameter tells the intensity or the different carbon nanotubes that you can separate, and thanks to chemistry that it is possible to really purify these different carbon nanotubes when they are suspended into a common solvent. So, this is how it is isolated, and little bit more into the discovery of carbon nanotube. The whole transition from fullerene to carbon nanotube came because of this microscopist Dr. Sumio Iijima from Japan. He is in the NEC center, and this is how it was to be when he was studying the material deposited on cathode during the arc evaporation of synthesis of fullerenes. He found that the cathodic deposit contained a variety of closed graphitic structures including nanoparticles and nanotubes. So, this is a simple curiosity, and this is the mapping of such discovery. And what you see here, these are all close walled nanotubes, carbon nanotubes, and they are also multi walled, and this brought the curiosity about the discovery of carbon nanotubes. So, to start with, make two observations because these issues need to be told, that there is a role of serendipity, that is sudden discoveries which has played very heavily in this new family of carbon, and observation and insight along with relationship between mission oriented and curiosity driven research. So, each one is a classic example of the statements that I have made. Mission oriented research and being very careful when you stumble at a discovery, because that might actually transcend you to another discovery. If you are only concerned about that one single peak corresponding to fullerene, we could have just missed out on a whole rich chemistry of carbon nanotubes. So, this is a curiosity driven research, therefore, every single image that we record, every single spectra that we record is actually very important. Now, this is a cartoon which is actually a simulation, but this shows the different polyhedras that the carbon can generate, and in this case you can see the 3 different polyhedra of carbon and hydrogen. One is a cubene type, another one is dodecahedron, and the other one is the carbon nanotube. This is exohydrogenated carbon nanotube. So, this is out of a simulation that we have developed just to show that there are 3 different polyhedras that the carbon can exhibit. So, let us take for in the first place the discovery of fullerene and what it really means. As I told you in the previous slides, this is a carbon with higher symmetry, and therefore, we call it 0 dimension, and the numbers that we need to remember here are there are 12 carbons with 5 membered ring, and there are 20 carbons with 6 membered ring in this buckyball, and out of which if you look at the edge sharing between the 5 membered ring and the 6 membered ring, there are 30 such edges and there are 60 such edges between a 6 membered and a 6 membered, and a 30 such edges between a 5 membered and a 6 membered ring. These are the features of this carbon. Why I am telling that is because when we try to bring out different chemistry or some new chemistry out of this fullerene, we need to understand in perspective where to attack, which carbon atom to attack. Therefore, it is important for us to know some of these coordinates, and this fullerene C60 is typically of the order of 7 angstrom, that is 0.7 nanometer, and therefore, the volume is around 180 angstrom. So, these are the numbers that we need to have in perspective. And how do we isolate? Because whenever a fullerene is made, you actually get a range of carbon soot which can have different fragments or different carbon clusters. So, the chief of this is nothing but C60, but it is also observed that C20, C30, C70 are all fragments that can be observed along with C60, which is the major product or which is called as the fullerene. So, one of the useful way to identify whether you have a very clean C60 or not is to use NMR, and here is a NMR of C13 which is recorded for fullerene, that is C60, and C60 will actually give you only one C13 NMR peak, and that is between 140 to 145 ppm. It is a very characteristic peak coming from a C13. So, if you have just one peak in C13, that means you have got a clean C60, but if you are going to have C70, then you would actually have 5 peaks coming in the same range, therefore, it is very easy for us to map whether we have C60 or C70 as a mixture, and in C70 you do not have the same sort of symmetry, Therefore, there are 5 different carbon centers in C70. As a result, you would actually find 5 peaks in C13 NMR. So, therefore, it becomes very easy for us to map whether it is a pure compound or not. And one of the best thing that can happen in this whole chemistry is the solubility, because it is otherwise very difficult to isolate carbon, and fortunately carbon 60 can dissolve in a variety of solvents, and as you see here I have listed very few of several common solvents have been explored, organic solvents, but these are some unusual solvents in which carbon 60 is soluble, and therefore I have recorded it. Reason is, in most of the common organic solvents like ethanol, methanol, dichloromethane or DMF or DMSO, the solubility is very negligible, of the order of sometimes 1 gram or less than 1 milligram per ml. Therefore, the most important one is 1-chloro-naphthalene, where up to 51 milligram you can dissolve in 1 ml, and as you can see here you get a very good purplish color of a solution which is devoid of any suspension. Therefore, it is possible for us to even make a film out of it, and this can be used for variety of other operations. And therefore, the solvents that we need to use whenever we get a carbon soot goes in this order: naphthalene based solvents, or as you see here dichlorobenzene, trimethylbenzene, xylene, carbon disulfide. All this shows very good solvent property for this carbon nanotube. One more thing that you need to understand in perspective is, there is another cartoon which clearly gives another possibility, that if you oxidize the fullerene, then this can actually become, if you hydrate this fullerene, then it can become a hydrated fullerene. As a result, you can make this even water soluble. So, this is a example of a hydrated fullerene which can improve on water based chemistry, which is environmentally also more preferred. Therefore, hydrated fullerenes are also possible when you try to carefully hydrate this fullerene molecule. Now, how does this fullerene come? Because when you try to synthesize fullerene, as you know, you try to use a arc plasma method, by which you try to get a sudden deposit of carbon from graphitic rods, and how it all happens, the proposed mechanism is as follows. Cyclic polyenes, what you see here, they can fold onto itself so tightly that the new carbon bonds can form, which is actually shown in the dotted lines. So, these are all C60 polyene actually can be bundled into this fashion, where new bonds come up and they curl up to give a C60 molecule. Other than that, because it is such a flash process, there is no way that we can generate or simulate how the bond making happens for this to happen, but this is the proposed mechanism for how the new carbon bonds can be formed. Now, what do we do with this fullerene, and where is the chemistry lie in this buckyballs? Actually, fullerene can be modified, and that is where the chemistry comes into picture. You just do not look at it and simply appreciate, but then you try to put lot of molecules or take out some atoms out of it and try to create rich chemistry in that. So, the substitution of these fullerenes actually can be viewed in 3 ways. One is exohedral fullerenes, where you try to put atoms or molecules or complexes on the top, on the surface of the buckyball or the fullerene. So, you call it exo. Another thing we can do, we can try to push some atoms or molecules in a preferred way, which can go and they can be held through a real charge transfer process. It is not simple physical existence, but there is a chemical phenomena happening between the molecules which are caged inside, and therefore, those are called as endohedral fullerenes. And another thing is, it is not just the fullerene playing a host lattice, where it can either do exo or endo, it can also be a guest, it not only a host, and in that case fullerene molecules can actually be pushed into carbon nanotubes. So, it can actually play a guest role also as much as it is a good host. So, based on these three divisions, several examples can be generated. This cartoon gives you an idea all the fullerene reactions that are possible. Especially C60 molecules undergo most of the reactions that we have listed here. Also C70 to a lesser extent may undergo addition type of reactions, polymerization type or substitution types of reaction, especially with the boron. Okay. So, just I would like to pull out a few examples. One is this buckyballs can be polymerized in this fashion. This can become very interesting. So, simple polymerization of this through extended linkages like this is possible. So, you make a polymer which can be dendrimeric or it can be linear. Therefore, polymerization of this is possible, and then I will take few examples to discuss. It is impossible to go through all the cycle. One is hydrogenation to fullerenes. You can completely hydrogenate it because there are double bonds in it, and then you can also make epoxides. This is a very reactive reaction where you try to treat it with oxygen in the presence of light, or we can actually do cycloaddition in this fashion, or we can actually have lot of host guest complexes, organometallic derivatives which can be generated on the top of the buckyball. So, several reactions are possible in this form, and we will take one or two examples to see how this can be done. Endohedral fullerenes, these are fullerene cages with encapsulated molecules which have many potential applications. It is construed that scientists will be able to engage a radioactive tracer and inject that safely into human body for mapping or for any spectroscopic investigation. For any radiation therapy, it is possible that we can actually use radioactive tracers to be injected into human body in a very safe mode, and that way fullerene is compared to be a very safe carrier, because you can put that inside and you can transfer it into the body. Another thing is, currently various molecules can be engaged in fullerene. For example, lanthanum can be put inside carbon cage, which is a C82 cage, and helium, which is a monatomic gas, can be put inside C60. Therefore, even putting preferred metal ions depends on the cage that you are looking for. For example, lanthanum cannot be easily put into C60 because of its dimension and other physical properties that may become intricate. Therefore, it is also to some extent selective, and similarly you can put scandium in C66 cage. So, it is possible, but in those cases the product yields are actually less than 2%, and in endohedral fullerenes there are a lot of information that we can get. For example, metal of fullerenes, there is a charge transfer between the cage and the enclosed metal, as in the case of scandium that is put inside C66. So, many rich chemistry can be verified as to what really is the interaction. It is not just a bound pair, but something unusually happens to this endohedral fullerenes. And for a review, actually we can go through article by Professor Dunch. These are again two examples of exohedral fullerene, and this is from a C60 molecule which is actually capped to osmium metal here, and this osmium metal is bound to 2 pyridine rings. So, you can actually get a exohedral fullerene using osmium, and this can be put in this apical position here, or we can actually use iridium metal center also, and iridium carbonyl, this is a carbonyl moiety and chlorine attached to it with other aromatic rings. So, this sort of exohedral fullerenes have also been attempted, and if you find out this exohedral fullerenes actually has a very potential application as hydrogen carriers, and therefore, it is being explored very richly for application into hydrogen storage, because this osmium or iridium metal centers can actually bind dihydrogen species, and they have a special tendency to exchange this dihydrogen, give up and also to retake, and therefore, when it becomes a reversible process, then it is a very useful material for hydrogen storage. And what US Department of Energy forecast is they just need a 9 weight% hydrogen storage density in any material, and 9% is enough to drive any automotive vehicles. So, it is found that organometallic molecules based on C60 and boron, which is doped, seem to have special affinity to dihydrogen species, that is molecular hydrogen. So, you can try to take it. Complexes of transition metals with hydrogen, they also can take. Only thing, these transition metal complexes, they actually polymerize when the dihydrogen species is removed. As a result, it is a irreversible one, and that is not the chemistry behind hydrogen storage. So, if you want a hydrogen storage material, then you need to be able to liberate the hydrogen and also selectively take it back, otherwise this cannot be a useful candidate, and in such cases scandium hydrogen species which is attached to C60 has been found to be a very good complex. This leads to stable species which can reversibly absorb additional hydrogen. So, this is one of the candidate which is being explored for hydrogen storage applications, and same I have tried to show you through this view graph. You can see here scandium metal center which is able to bind a rich amount of molecular hydrogen species here, and this can become reversible. So, we can put it and take it back. Doping with boron becomes very important in this case. So, this enhances the complex stability by increasing the binding energy, and this allows the binding of an additional hydrogen molecule per scandium, increasing the amount of retrievable hydrogen, and this is actually a paper found in Physical Review Letters in 2005. Now, the other chemistry that can happen from fullerene is that you can get into the carbon nanotubes, and therefore, fullerene, when it is endohedral fullerene, they can actually serve as a carrier which can be filled into open sided carbon nanotubes. So, single wall carbon nanotubes encapsulating C60 is also there. Only thing, achieving this is a very tricky thing, although theoretical studies they show that to put fullerene into carbon nanotube it takes only 0.37 electron volt, which means it should actually happen at room temperature, but so far studies have not been successful where people have tried it up to 350 degrees in vacuum. So, here is another example where the Russian group they have tried to attempt at room temperature. Only thing, the yield is less than 1%. Adding single wall carbon nanotubes to a saturated solution of fluorine has been attempted, and vice versa, taking fullerene into a saturated solution of single wall has been attempted. And one approach which has given dividends is, it is almost like a brute force where you try to use high pressure. So, here is supercritical carbon dioxide which is used, and using this under high pressure for 10 days they were able to dope successfully fullerene into carbon nanotubes to the order of 30%. So, it appears that with more of high pressure it is possible to do this nano peapods sort of synthesis. So, this has also been attempted in the recent past. These are some of the examples of how different derivatized fullerenes can be made, and these are specially candidates for HIV properties, and this has appeared in bioorganic medical chemical letters, chemistry letters, and this has come out in the year 2005, where they have found especially the geometrical ones, the trans and cis isomers, they have a very selective response to HIV virus. So, this exohedral fullerenes are specially candidates which can have specific activity, and here is another example where we can try to make dendrimers out of fullerene. So, you have the fullerene moiety here, but you can actually attach such first generation dendrimers. So, as a result you can actually get a very macroscopic molecule, and this is specially useful because it turns out to be totally water soluble. So, this has specific applications, therefore, such molecules also have been prepared in the recent past. And lastly, on fullerenes, I would like to mention that fullerene is not just about a substitution, but fullerenes with doping with potassium ions have shown a extraordinary property of superconductivity. So, this is a superconducting potassium doped C60 K3C60, which actually shows a TC somewhere at 19 K. But what you would see here, if you try to replace this small cation potassium with rubidium, or then rubidium you can put and translate it with cesium, you can see that the lattice parameter of this C60 is changing from 14.2 to 14.6, and as there is a expansion, you also in the crystal lattice you also see that the TC is varying. So, this has been attempted, and this is one of the extraordinary response of fullerene in terms of its electrical properties. So, just carefully dope it with the monovalent ion potassium, rubidium, cesium, anything you can translate it, and these are not just a fluke method, it has been characterized very clearly that it seems to have a very definite dependence on carrier density. So, depending on the carrier density the TC can be altered. So, fullerene has specially hit the superconductivity map mainly because of its substitutions around the carbon cage. Apart from this phenomena of superconductivity that is seen in fullerene, another important application is also in the area of photovoltaics. As you would see here, this is called as PCBM, which is a very well known candidate of C60, which is nowadays used as a blend along with a fluorine polymer. This is the fluorine base with different substitution. In this case it is with the benz dithiazole, and with such molecules it is possible for us to make a blend where you actually get a donor and an acceptor, fullerene as a acceptor and the fluorine as the donor. So, you can actually make a heterojunction polymer, and this is the SEM view graph of how a polymer blend will look like. You can see that you get a very continuous spread of a amorphous polymer film, and what you can clearly see is that this is the PL, this is the absorption and PL of the fluorine moiety, where you can see the fluorine absorption is somewhere around 500, maximum at 500, but once you make the blend you can see that it is actually blue shifted, which means it is shifted to higher energy. Therefore, this will become a very efficient blend for photovoltaic application, and this is the view graph in the inset, which gives you approximate clue to how this sort of heterojunctions can behave, and this is in dark and this is the IV curve in light, and you can see that the open circuit voltage OC and the fill factor is quite decent here and carries a good amount of current density. So, the latest application of fullerene, although it is not being talked about as much as carbon nanotube, but it is actually playing a very silent role in terms of becoming a very useful electron acceptor in photovoltaic devices. One last example before I finish on fullerene is the water soluble fullerene derivatives, which has been found to have antiviral activity, and especially in terms of treating with this sort of virus, forest virus or stomatitis virus. What has been found out is, if these viruses are blended with water soluble fullerene, and if there is a visible light illumination, with respect to the illumination time, you can see that the virus level is rapidly coming down, and this is with addition of C60, and without the addition of C60 you can see the response, and without light you can see the response, and with light with C60 you can see a tremendous influence on the antiviral activity. So, carbon 60 or fullerene seems to have a very peculiar response to biological applications also. The chemistry there is, this effect is attributed to the generation of singlet oxygen, which actually will impair the viral activity. So, it is the singlet oxygen that is generated which is responsible for this antiviral property. So, in summary of C60, we can say C60 buckyball was the first fullerene that is discovered, and it is the third form of pure carbon, which is next to graphite and diamond. But this summary is inconclusive because we have the other new ones which have come into picture. Variations of fullerenes include exohedral, endohedral and nano p pods, and synthesis challenges still exist for all the variations of fullerenes because the mechanism of formation is still unknown, and potential applications are now envisaged in the field of medicine, nanoelectronics and in energy, of which I have given a representative example. Now, having said this, I have to confess that this is a very limited scope in which I have tried to tell about the chemistry of fullerene, but there are several literatures in the websites. There are several useful links which can give us tremendous information about the chemistry of fullerenes, which I will be listing in the slides at the end of the lecture. Therefore, I encourage that the readers can go through that. Now, we will focus our attention on carbon nanotubes, and this carbon nanotube is a one dimensional carbon nanotube, and we can see how this carbon nanotubes evolve from the basic structure. As you would see here, there are two cartoons which I have projected here. One on the left side on the top is a single wall carbon nanotube, which you can easily map it around, and this is just a picture of graphene which is actually rolled up. So, that is the easiest way to visualize how a carbon nanotube is evolving. And then on the right side you see this is a multi-walled carbon nanotube. So, several walls are there, which means one small carbon nanotube got fixed to the other and then to the other, therefore, you can actually go for several walls. So, it is called multi-wall nanotubes, and there can be just 2, there can be even 7, there can be 4, depending on the process that you adopt to make these compounds. So, as you see here, the way the single wall nanotube can be easily envisaged is that you take a 2-dimensional graphene sheet, which is nothing but a single layer of graphite chopped laterally, and then you just try to roll it, and as you roll it you will come across a single wall nanotube. But the point is, the way you try to roll up the single wall nanotube will end up in different electrical properties of the single wall nanotube, which I will try to list it. Now, the way we can try to roll up this depends on the unit cell or the way we map it. For example, let us take the case of this axis. If you try to draw a line, and this is a CH vector. Now, in this we can express CH as N A1 plus M A2, where A1 and A2 are unit vectors of graphene in real space. So, the way we mix these numbers N and M will matter what sort of carbon nanotubes we can get. For example, in the case of N0, what you see here, N0, this relates to a zigzag carbon nanotube. If it is going to be along NN, it is called a armchair nanotube. So, what does this mean? Here this is going to be 1 0 and this is going to be 2 0, that is what we mean by N0, okay, and this is going to be 3 0 and so on. So, if your axis or your vector is going to lie on N0, then you would actually get a zigzag nanotube, and if it is going to be, for example, here in this case this is 1 1, and in this case this is 2 2, and in this case this is 3 3, and here this would be somewhere around 4 4, then we are talking about a N armchair. So, the way you roll it up matters with respect to this CH vector, and that will determine what sort of nanotube you get and the corresponding electrical property, and that is what we see here in this cartoon. So, if you have an armchair which is nothing but your 1 1, 2 2, 3 3 and so on, then the alpha that you generate with respect to this alpha is going to be 30 degrees, and in that case actually you would end up with your armchair configuration. And if it is going to be 0, which we saw in the previous cartoon, that is your 1 0 0 2 0 1 0 2 0 3 0 4 0, then you get across zigzag, which is alpha is equal to 0 degree, or it can be also a intermediate one where your A is not equal to B. In that case the angle can vary between 0 to 30 degrees and you end up with other configuration. So, based on the way you scroll your graphene sheet, you can either get a zigzag one which is metallic in its nature, or it is a armchair which is semiconductor in its nature, or it can be a chiral one which is semi metal in nature. So, carbon nanotube itself brings about lot more complexity by the way it is arranged. So, it can result in different dimensions, it can result in different configuration, it can result in different property. Different dimension, I mean it can be single walled, it can be multi walled, and it can have the diameter which is different, and as you see here the way you roll it, you can also expand the dia of your nanotube, and this also affects the electrical conductivity. So, you can also get a metal, you can also get a semiconductor depending on this. So, the whole issue of carbon nanotube revolves around which one you selectively get and what is the method that you use for getting such selective ones. And as you see here, this is another cartoon, just tells you if you are going for a armchair, then you look at the edges how they reflect, and if you are going for N0 you can look at the edges how they transform to be. So, just by looking at the way it is scrolled you can decide on the configuration, and depending on whether it is a zigzag or whether it is armchair, it is also possible for you to get a different sort of dimension of your carbon nanotube, and in this case you can see the TEM microscopy, which clearly shows the TEM image shows this sort of structure. That means this is a single walled carbon nanotube which has a dia of 1.37, and here you have another one which is called a double walled. Okay, this is one wall and this is the outer wall, so we call this as a double wall. Okay, so this double wall stuff is also possible, or you can see this TM image which actually has more than 4. So, this is a multi-walled nanotube. So, in essence when you look at the literature, you can actually see this abbreviation quite a bit. SWNT or MWNT both are referred to as single wall and multi-wall nanotubes. For certain applications multi-wall is more than enough, but for certain preferred applications you always desire to get a single wall nanotube, which is a challenge. Just to draw your attention to the electrical properties and why so many literature outputs have come on carbon nanotubes, let us just make a lighter comparison between the different forms of carbon, then we will get to know why this research is still a very intense activity. Now, if you take the property and compare with the different carbon forms, you can see here specific heat, this is comparable to diamond. Thermal conductivity, if you observe, the thermal conductivity of single wall is much higher than diamond or graphite. Therefore, from thermal conductivity point of view, single wall nanotubes are really most preferred. Electrical conductivity, again you can see for graphite it is 900 to 1700 Siemens per centimeter, whereas in the case of carbon nanotubes it is almost comparable or even double than the graphitic form. Therefore, in terms of electrical conductivity it holds a lot of promise, and then the same is true for thermoelectric also. You can see the thermoelectric power at 300 K is around 3.5 for graphite, whereas it is 22 for single wall nanotube. So, you name any physical property, there is a very distinct difference between either graphite or carbon nanotubes or diamond with carbon nanotubes. Therefore, there seems to be in essence some curiosity on almost every property that we are looking at. Now, how do we make this carbon nanotubes? Three important methods are there which I would like to highlight. One is arc discharge method, another one is chemical vapor deposition, another one is laser ablation method, which is a vaporization method. So, in arc discharge you actually bring two graphitic rods, you apply very high voltage and a plasma generate, then all the carbon suits are trapped in alkane, and then we can try to isolate different fragments of carbon nanotubes. So, that is the way it is done, and then we can actually produce single wall and multi wall carbon nanotubes with few structural defects, and then tubes tend to be short with random sizes and direction, which is the limitation of your arc discharge method. Whereas in chemical vapor deposition you place a substrate in oven, heat it to 100 degree and slowly add the carbon bearing gas, usually acetylene is sent, and in that case it frees up the carbon atoms which actually combine into carbon nanotubes. It is the easiest way to scale up to industrial production, and the only problem with the chemical vapor deposition is it actually induces lot of defects. Okay. And then we can look for the most sophisticated one, that is laser ablation, blast the graphite and then try to trap the carbon that is coming under various conditions. Primarily this gives selective single wall carbon nanotubes, but the problem is it is more expensive and it requires more sophisticated infrastructure. As a result, people usually prefer either arc discharge or chemical vapor deposition, which is much more versatile. and these I have included just to give you an idea about what this arc discharge is. You have the two graphite rods and this is actually kept in vacuum in helium atmosphere, then you get the discharge and trap the carbon soot, or we can actually shine the laser to graphite rod and then we can trap the soot in a water cooled copper collector, or we can actually take a silicon dioxide wafer and try to put some nickel film on that and then run it through hydrocarbon, and when this is heated then this would actually decompose the hydrocarbon to carbon nanotube on the nickel metal. So, these are various ways of getting this single wall carbon nanotubes or multi wall carbon nanotubes. This one I have specially included just to show how people have become obsessed with the carbon nanotubes. As you can see, for those who are really working on this, it can become an obsession like a doll, and this person here is actually holding such a 3-dimensional model. So, you can see how it can become so close to your heart when you try to work on carbon nanotubes. You can see the simulation pictures which show how this carbon nanotubes can be tagged to something, and this is another view graph which shows about carbon nanotube forest. Look at the way laterally they are grown, bundles of carbon nanotubes can be formed, and these are called as carbon nano worms, you know. So, there is so much of chemistry which is rich, and several groups are actually working into probing the interesting aspects of carbon nanotube. So, I will stop here and try to deal with this in the next lecture, especially on the chemical properties of graphene and also on single wall carbon nanotubes.